Okay, welcome back. It is finally time for day 22 of Advent of Code 2022. Yeah, this is probably the third or fourth time I'm trying to make this video. One time the audio wasn't working, so I did the whole thing. I went through it, I talked and I talked and I talked and I talked, and then I realized that the audio wasn't, I hadn't recorded any audio. And then I tried to do it again, and then I wasn't happy with the illustrations that I had, and so on and so on. Yeah, illustrations, you have no idea. But now I'm back with where my whiteboard is, so now we can do this. All right, so let's dive right in. Advent of Code 2022, day 22. Okay, monkey map. The monkeys take you on a surprisingly easy trail through the jungle. They're even going in roughly the right direction according to your handheld device's Grove positioning system. As you walk, the monkeys explain that the grove is protected by a force field. To pass through the force field, you have to enter a password. Doing so involves tracing a specific path on a strangely shaped board. At least you're pretty sure that that's what you have to do. The elephants aren't exactly fluent in monkey. The monkeys give you notes that they took when they last saw the password entered. This is your puzzle input. For example, and then we have a map right here with some open spaces and some rocks and some stuff, and some instructions down here. But let's take a look. So the first half of the monkey's notes is a map of the board. It is comprised of a set of open tiles on which you can move, drawn as a dot, and solid walls, which are tiles that you cannot enter, drawn as pound signs. The second half is a description of the path you must follow. It consists of alternating numbers and letters. A number indicates the number of tiles to move in the direction you are facing. If you run into a wall, you stop moving forward and continue with the next instruction. A letter indicates whether to turn 90 degrees clockwise or counterclockwise. Turning happens in place. It does not change your current tile. So, a path like 10R5 means go forward 10 tiles, then turn clockwise 90 degrees, then go forward 5 tiles. You begin the path in the leftmost open tile of the top row of tiles. Initially, you are facing to the right, from the perspective of how the map is drawn. If a movement instruction would take you off the map, you wrap around to the other side of the board. In other words, if your next tile is off of the board, you should instead look in the direction opposite of your current facing as far as you can until you find the opposite edge of the board and then reappear there. For example, if you're at A, here, facing to the right, the tile in front of you is marked B, way over here. If you're at C and facing down, the tile in front of you is going to be marked D, up here. It's possible for the next tile, after wrapping around, to be a wall. This still counts as there being a wall in front of you, so movement stops before you actually wrap to the other side of the board. By drawing the last facing you had with an arrow on each tile you visit, the full path taken by the above example looks like this. You see, follow, go to the right and down and to the right. Go off of the map and then pop back in here and go down to the right, and yeah, we end up right here. To finish providing the password to this strange input device, you need to determine the numbers for your final row, column, and facing as your final position appears from the perspective of the original map. Rows start from 1 at the top and count downward. Columns start from 1 at the left and count rightward. In the above example, row 1, column 1 refers to the empty space with no tile on it in the top left corner. Facing is 0 for right, 1 for down, 2 for left, and 3 for up. The final password is the sum of 1,000 times the row, 4 times the column, and the facing. In the above example, the final row is 6, the final column is 8, and the final facing is 0. So the final password is 6,032. Follow the path given in the monkey's notes. What is the final password? All right, this first part was not too bad. Let's take a look. Okay, so we have our part A. We load all the data, and then we call our parse data file. Let's take a look. Parse data. We start by splitting by double line feed, which gives us map data and the instructions in like split up like that. Then we have our M, which is going to be the map. And then we just split lines and add lines from the input to M. No funny business there. And then we make sure that all the lines are the same length, because that turns out to be a little easier later on. Then we go through the first line looking for a dot, so a defined space within the map, and that becomes our current position. The raw instruction is pretty straightforward. We go through it. If we see a digit, we add it to a buffer. If we see something that's not a digit, we turn what we have in the buffer, if anything, into an integer, store it in an instructions array, and then we add the instruction. So if we have 10R5, as in the example, we would first see the 1 and then the 0, and they would be added to the buffer. Then we would see the R, and that would add the 10 to the instructions, and then the R, and then the 5, because we make sure that at the end, if there's anything left in the buffer, we turn that into an instruction and add it. So we return the map, our current position, and the instructions. The little squiggly here is because theoretically this is like inside a loop and inside a conditional, so the language server doesn't know for sure whether this will ever actually be set. But we know that it is, so we take the chance and just return it. Cool. All right. So we create this little directions list, which has all the different directions and the order in which they, and in an order where if you are turning to the right, that means you are moving forward, wrapping around, of course. And if you're moving left, or if you're turning left, then you go back one in this in the list. So this here is to the right, and if you are pointing to the right and you turn right, you are now going down. That's down, and so on and so on. So that's what the directions does. Okie doke. So we start by facing right as per the instructions, and then we go through the instructions one by one. If it's an integer, that means that we have to move in the direction that we're already facing. And that's what we have here. So let's take a look at make move. It's very simple. While true, so because we might end up in this no man's land where that's part of the map that's not defined, so it's not part of the grid that is not part of the map. So part of the grid where that's blank. So that's what we get here. We calculate the new position, taking our current position and adding the direction. If it turns out not to be blank, that means that it's either a dot or a pound sign. And then we break and we return our new position. If we end up in a place where there's no, that's empty, so it's not part of the map, we just keep going in the same direction. So this loop keeps going and we keep adding the direction vector to our position, and then we end up in a new position. And then we return the new position. And back here in our main function, the part A function, we check if this new position is a wall, in which case we break without updating our current position. If it's a dot, means it's a valid position, then we update our current position to be this new position. And if it's anything else, then we panic, basically. Again, I try to do this almost always if there's any doubt about what we're going to see. If it's not an integer, then all we have to do is update our current direction. And as I mentioned before, if you are turning to the right, you just have to move one in this direction in this list. Because if you're already facing right and you turn right, you're going to be facing down. If you're facing down and you turn right, you end up facing left. If you're facing left and you turn right, you end up facing up. And, vice versa, obviously, the other way around if you're turning left. And yeah, that's all there is to part A. We just keep going, and eventually we end up in a position and facing, and then we get the score, and boom, that's it. No big deal, right? For day 22, that was pretty easy. Yeah. So let's let's take a look at part B, because that's the killer. All right, part 2. As you reach the force field, you think you hear some elves in the distance. Perhaps they've already arrived. You approach the strange input device, but it isn't quite what the monkeys drew in their notes. Instead, you're met with a large cube. Each of its 6 faces is a square of 50 by 50 tiles. To be fair, the monkeys map does have 6 50 by 50 regions on it. If you were to carefully fold the map, you should be able to shape it into a cube. In the above example, the 6, smaller 4x4 faces of the cube are like this. So face 1, 2, 3, 4, 5, and 6. And if this looks kind of weird, like in terms of dimensions, remember that most fonts are twice as tall as they are wide. So it's a little map projections, they're always inaccurate. So this is no exception. All right, you still start in the same position and with the same facing as before, but the wrapping rules are different. Now, if you would walk off the board, you instead proceed around the cube. From the perspective of the map, this can look a little strange. In the above example, if you're at A and move to the right, you should arrive at B facing down. That's here. So you walk off the map, and strangely, you appear here facing down. If you're at C and move down, you would arrive at D facing up, where C is here, and that brings you over here. Obviously, right? Anyway, walls still block your path, even they are on a different face of the cube. If you're at E facing up, your movement is blocked by the wall marked by the arrow. So here you're trying to move up, but because this side here meets this side here at this point, you're going to get stuck. So that means you remain at E. Using the same method of drawing the last facing you had with an arrow on each tile you visit, the full path taken by the above example now looks like this. Look at this madness. So you go right, then you go down. So you go from this side of the cube to this side, but because you're still on the map and nothing special happens. And then you turn right, and from there you appear down here. You go this way, that way, and then from here you come, you arrive over here, and then make your right, and then go up. And that's your final position. And just like before, the final password is still calculated from your final position and facing from the perspective of the map. In this example, the final row is 5, the final column is 7, and the final facing is 3, so the final password is 5031. Fold the map into a cube. What? Then follow the path given in the monkey's notes. What is the final password? And oh my goodness, I don't usually really take notes. You saw a couple of times I used the whiteboard a little bit. Nothing like this one. This one was bananas. I have let's see. Yeah, we start way back here. Look at this nonsense. Just pages upon pages upon pages upon pages upon pages. I mean, you can barely see it. So there's all this stuff. Me trying to figure out, how these things work, because, well, there we go. Look, there's just all this stuff here, and so part of my biggest problem here was the fact that, how I always like to, I use the sample input, I do the algorithm, and I check if the sample, if I get the output as expected using the sample input. The problem here is that, see this sample input right here? Look at the shape of it. Whereas mine is shaped like this. So any implementation that would work for the sample wouldn't work for the real input if I did what it appears most people do, which is to actually cut it out, make a paper cube and then try to figure out that if you're moving from this side to this, then it changes like in this and this way. And I don't know. I don't have the focus to do that. I knew that I was going to mess it up, at least for one of them, right? And I had to get it correct for both the sample and for the real input. And there was no way I was going to get that right and get the algorithm right. So I would have, I would have a like translation table of some sort for the sample, for the real input, and an algorithm. 3 things that could be wrong in different ways, and trying to debug that was just I thought that was going to be a nightmare. But it turns out that trying to do this the proper way, where you don't make any assumptions, is not much more pleasant. So yeah, let's take a look. It turns out that these cubes can actually be folded up in a lot of different ways. Like there are all these ways here, right? And yeah, trying to find out what we can reason about these cubes was a challenge. Let's I'm on the way here. Okay, let's take a look. All right. I hope you can still hear me as I'm doing this. I'll turn this up a little bit. Let's take the sample input. So this is the map from the sample input. So what I had to do was, there was a couple of different parts to it. So I divided into these regions, so I know that these are the sides, and then I stared at it for a long time, trying to see if there was anything that I could say with some certainty that would always be true. And I realized that if you have a corner like the one right here, like this is a concave corner, as opposed to a convex corner, which you have up here, right? So this is concave because it bends in. And whenever you have a concave corner, you have something that because you know that no matter how you're going to end up folding this side right here is going to match up with this side right here. So if I go off this side in that direction, I know I'm going to appear here going in that direction, and vice versa, obviously. So that was a key insight, as it turns out. So that means I know what to do with these ones. I know what to do with this and this. And these two, let's number them: 1 and 1, and 2 and 2. We know that they're going to meet. We know that 3 and 3. We know that they're going to meet. And then I had to start. Let me see if I can get up here and stand up. Okay. Yeah, that only got me part of the way. There are obviously more sides than this, and trying to just staring at it for a long time didn't really get me that far. I worked out that if I fold this up, this side right here would meet this one. And based on that, I came up with a theory that maybe I could start from a concave corner and work my way out. So, because I knew that I just started putting in information that I knew, or information that I could identify. And then I realized that starting there, I can move out. And then I thought, well, heck, what if I can do that all over the place? So why don't we get this number 5 and get this number 5? And we knew from one of the examples that this was true. So this side here does meet this side over here. And then just kind of haphazardly, I assumed that was always going to be true. And that means that I could assign 6 to these two, because that's one step and another step away from a concave corner, right? You have 2, 2, and then you're one step away, 6, 6. And then, how about that? You end up with 2 sides that are left, and obviously they're going to meet. So, yeah, I was pretty happy with that. 7, 7. Okay, so I figured start from outline the map here. You find the outline, find concave corners, and then work your way out from the concave corners, and then there's going to be a pair left, and they have to meet, right? So I got it, and I worked it all out, and I was super happy with I was super happy with myself that I got it working. But then this sucker appeared. So let's see if I can draw it correctly. Okay, so we have 2. And go down. Like that. Please apologize with my drawing skills. That's right, isn't it? Oh, whoops. Does that fold up? I think it does. Yeah. Okay. So if we try to use the same method here, so we get these 2 concave corners. They're obviously going to meet. Easy peasy. Then we got number 2 here, and we got number 3 here. Oh, this is easy. Plenty of concave corners to work with. Yeah. Great. Because now what? Right? I can't start moving out from number 3 here, right? Because I'm gonna meet number 4, and this is gonna meet that one. We know that, so it can't also meet this one up here. So I can't start from this concave corner and work my way out. Can't start there because same problem. Can't start here because same problem. Can't start there because same problem. So, well, shit. Right? But I finally realized that if we, instead of going out from these corners, what we do is we sort of collapse these, and we collapse both of them. So we know that these will meet, and then we have the next ones out from there, which gives us, that was the working theory, at least. So this is what I tried. And then I finally end up with like the 2 that are left. And I don't know, there's probably some kind of proof that this is correct. I didn't come up with one, but I tried. I did a couple of different configurations, and it seems to do the trick. So that's the strategy here, right? We no. Oh, boom. Yeah. So the strategy is basically that we come up with the outline all the way around, and then we identify the concave corners. And once we have the concave corners, we collapse them one at a time, and we find the neighboring ones, and we just keep moving out from those known sides that are pretty easy to reason about. And yeah, it took me a couple of days, and obviously a lot of drawing, a lot of notebooking. But okay, let's see what I came up with. I'm not proud of it. I'm a little proud of this, working all this stuff out, because everyone else, that all the smart people that I take a look at their solutions once I've done my own. All the ones that I could find were doing manual stuff. So they have, in the comments, they'll show what their map looks like, and they do I'm on the side of this, then I go right, then I end up here, and blah 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 blah. But no, I got real stubborn, and I did it without making any assumptions about the shape, as far as I know. So kind of happy with realizing that. Not very happy with my implementation at all. And this is after a lot of back and forth. And multiple of these videos that didn't work out, where I found like small mistakes and tried to fix them. But geez, okay. But let's take a look at this. Same parse data, we get all the same stuff out. But then we build our translation map. So we start by generating a list of all the regions. So what we do is, let's see, wait. We create a coordinate system. So if you can kind of imagine this coordinate system going, that's really not. Yeah, so that's 0, 1, 2, 3. No, doesn't matter. 0, 1, 2. So this region right here is called 0, 0. This one right here is called 1, 0, 2, 0, 3, 0, 0, 1, 1, 1, 2, 1, etc. You get the idea. Cool. Okay, so that's all the regions. And obviously it depends on the cube size. So let's take a quick look at get all regions. So we go through the map, jump a cube size each time, and check if it's not a space. Because if it's a space, then obviously it's a part that's not actually part of the shape, but it's still in the like the coordinate system that we have that spans the whole thing. And then we return all those regions. That's pretty straightforward. Okay. Then we create our translation map. Optimistically, because it's going to be a little while before we're ready to populate it. So we find all of the edges. So this is not a graph. We can probably model it as a graph, but that's not what we're doing here. It's not that kind of edge. These are outer edges of the shape. So just like a couple of weeks ago where we had the cubes and we wanted to have a way to identify the sides of the cube, what we do is so that we can have a unique way to identify them, is that we use the coordinates of the coordinates of a square, and then if it's for a horizontal square, we use the coordinates for the one that's sort of above it, and then we denote that it's a horizontal one by saying this one here is 0, 0, for the square, or the region as we call it, and then 0, 1 because it's it's below, right? So that's how you get there. And right for this one, it's going to be 1, 0, and then 1, 0 for the direction where it is. So we never deal with like the left edges. It's always a right edge of potentially an empty square. But that gives us a unique identifier for each possible edge here, and that's what we have here. So we go through all the regions, and for each region we look in all the different directions. And if we're in any one of these and we look in any direction and we don't see, if we're over here, we look there, and this is not part of the map, we know that this right here is going to be an outer edge, and that's what we store right here. Okay, so now we have all the edges, and then the next thing we have to do is find all the concave corners. So what we do here is we take, for each possible edge, we get all the possible corner edges. So if for instance this was the edge that we're looking at, like this one right here, it can form a corner with this edge, this edge, this edge, or this edge, right? These are the only ways that this well, that's a dumb example because it's not an outer edge, but this this side right here, this joint right here, whatever you want to call it, can form a corner with this one or that one or this one or that one. And that's what we get back from get possible corner edges. We can take a quick look at it. Yep, it says right here in the comment, return all edges that this edge could form a corner with. So yeah, it takes the coordinates of the region and then the direction, like for let's say for this specific edge right here. That would be 1.1 for this square, for this region, and then 0,1 because it's the bottom one. It's one towards like the 0,1 direction. So that would be that one, and it would then, yeah, that's what this one does right here. It goes in the different directions and yields the possible edges that it can form a corner with. All right. So it does that for each edge. So it looks at an edge part, one of these chunks right here, right? And for each of them, it finds all the possible corner edges. And if any of those corner edges is in the edges set, that means that it's an actual edge, and that means that we have a corner, because we're only considering edges that might form a corner with our edge 1. And if edge 2 is in edges, that means that it exists, and that means that we have a corner. And then we have to determine if it's concave. And yeah, pretty surprisingly, the direction actually doesn't matter. So yeah, all we need to do is get the maximum of each of the coordinates, and if that's not in regions, that means that they are concave. And don't believe me? I don't blame you, because I did not believe it. There was a lot of head scratching. But I went through all this. Check this out. All right. We have these 4 configurations right here. I hope this makes sense. So this is basically what I drew up here. So we have the coordinates, the x coordinates and the y coordinates, and then we have like these 4 different configurations. There are 4 different ways that you can have a corner, right? They can face in all those 4 different directions. So in each one of these, we have a concave and a convex corner. I think the probably easiest if we just zoom in a whole bunch. So this right here, this corner, that's the concave corner, and this up here is convex. So, and the same over here, concave and convex, concave and convex, and concave and convex. Okay. And yeah, I just go through all of them. You can go through this if you want. Basically, yeah, just all the valid regions in the first one is 1.1, 2.1, 2.2, 2.1, 1.2, and 2.2, etc., etc. They're all listed here. And yeah, I just listed all out that, the concave corners, so and so and so. And it turns out that for all of these examples of concave corners, max of x and x1 and x2, comma max of y1 and y2 gives us all these, and neither of these are valid regions. And if it's a convex corner, max of these is in regions. I'm sure that makes sense, and somehow I couldn't be bothered to work that out. But trust me, I checked this. It's yeah, I think this is solid. Okay, let's jump back to here. All right. Yeah, okay. The squiggly lines in this case is because it doesn't know for sure how many arguments star edge1 and star edge2 is gonna turn into. It doesn't matter. If it turns out that the corner is concave, then we add it to the set of concave corners. All right. Then we have this little function right here that we'll need in a second, which takes so if we look at this edge, for instance, the way that the unique representation for this edge right here is 3, 1, which gives us this region right here, and then the direction down, which gives us this one right here. But for the rest of this algorithm, it turns out that it's for the rest of it, it's really handy if we can tell which region it belongs to and which direction it's actually in. So this side right here, I mean, it's a lot more natural for us to think of it as the upper edge of this region right here, rather than the bottom edge of this empty region right here. And given like the unique identifier for an edge and the list of regions, we can determine if we can get the we can go from 3, 1 down to 3, 2 up. Okay, that is what this function right here does. Okay, so as we saw when we were looking at it, we always work out in pairs. So we start from concave corners, then we go out one. And that's what we are doing here. So we take the two edges from the concave corners. We calculate the region and direction. So just like I just explained. And then we add that to our translation map. So, first thing we're adding to the translation map. So the key we use in the map is the region and direction, which turns out to be really handy because when you're actually making the moves, you just want to know I'm in this region and I'm going in this direction off of the map. Where am I going to turn up? And that's what we're doing right here. So we know that region 1, direction 1, meets region 2, direction 2, right? So 3.2, no, 3,2 up meets, pointing without looking at the board is hard. There. 2,1 right. Right, these two right here, this one and this one, are gonna meet. So if you are going right here, up here, those are, that's where you're gonna end up. That's what these translation maps do. Okay. Then we add that, that set of, or those two edges to the list of current pairs. So current pairs are the ones that we are currently looking at and trying to move out from. Okay, so we record all the edges that we've already handled so that we don't handle them one more time. Oh, yeah, and then there's this whole mess because it turns out that, as I explained when we saw that one up there, sometimes it doesn't work out that way because you can't, you're going to end up with conflicts if you just try to only use the concave corners if you don't join them up. So that's what this next step does. It joins them up. And it's a mess. So for each of the concave corners, we look at each edge, then we create a set that only contains the buddy, like the other edge that's part of this specific concave corner. Then we have get possible corner edges and subtract the other edge. So suppose we're looking at these two edges right here. We look at one of them at a time. So we have the pair, and what we want to do is we want to go from this edge and out. And we want to go from this edge and out. And then try to see if we meet any other concave corners that we can kind of fuse with, or whatever you want to call it. So we start by, we look at all the concave corners. So the set of these four, that one, that one, that one, and that one. And, pick one, right? So we start with this one. And then for each of these two edges, we look at it and we subtract, from the set of these two edges, we find the other one, because we want to remember this one in a minute. Then we get all the neighboring edges of this guy right here, and we subtract this one right here. And then whatever is left, whatever that is a valid edge, has to be like a neighbor. Then we check if one of those, if that neighbor happens to be part of a concave corner. If it does happen to be part of a concave corner, we get the full corner, subtract this guy to get this guy, because this guy and this guy are now a pair that we have to start from and move out. And the same with this one. This guy right here becomes a pair with this one and move out. And then we have the one that's left that is a tiebreaker. Yeah, so that's what happens here. It's terrible. So we go through all the corners, and for each edge we subtract ourselves from the corner. That gives us the other edge as a set this time. And we look for additional neighboring edges. So we get that intersection. If there is less than two, right, there doesn't have to be one. There might not be any. Or there might be one, like in the case that I just showed. I got surprised so many times during this implementation that I always like, I'm not going to assume that I'll never meet 2, so I put in this assertion, and so far it hasn't happened. But so if there is 1, that means we've found a neighboring concave corner that we need to fuse with. So comments are pretty elaborate here. We find the corner it belongs to, we determine the other edge of that corner, then we remove like the corner that we're looking at right now and that neighboring corner from the current pairs, and then we add a new pair, which is like that other edge and the neighbor, and then we break out. Okay. You with me still? Jeez. Okay. So then the next thing that happens is we, like for any of the edges that we haven't looked at yet, or as long as there are edges that we haven't handled yet, we create an empty set of like the next pairs that we want to look at, and we'll go through the current pairs and try to move one out from there. That's what happens here. So we create a set called P, and then we go through, so we go through the 2 edges in like whichever current pair we're looking at. Then we get all of the neighboring edges of it, whatever intersects with the actual edges that are in our map, and we subtract all the edges that we've already handled. If that gives us a hit, then we add that to P. And then we do the same thing for the other edge in the pair, right? So that's what we're doing here. We're like, from here, we try to find if there's anything that hasn't been handled yet. From here, we try to find something that hasn't been handled yet, and we end up with these 2 in P. Now, that's not always the case, right? Because at some point, you might overlap, like you might meet the other one. So only if both find, like from the current pair, and you move one out, if in both directions you find one, then you check if, okay. So this line right here checks if we have any overlap with any of the other next pairs that we've identified during this iteration. And if so, that means that we found a corner that is the same distance from 2 different concave corners, because we met it at the same time, in the same iteration. And then we don't really know what to do, so we just throw it away, and then hopefully it turns out to be only one pair that we can't place using this algorithm. If we're out of next pairs, if this whole thing didn't identify any pairs, so if moving out we didn't find any edges that haven't been handled and that isn't at the same distance from a concave corner. If that happens, we check if we only have 2 left, and if we do, then we add those 2 as next pairs, because if those are the only 2 that are left, then easy peasy, then we add it. And once we have that, we go through the edges, and then we do the same thing with the get region and direction of outer edge, add it to the translation map, record that we've handled those edges, make these next pairs the current pairs so that we can move out from there in the next iteration, and that's it, right? Easy peasy. No big deal. Okay. That just gives us the translation map. Look at this nonsense. Okay. So now this part here is very similar to part A. We have our direction and we have instructions and stuff. The difference here is this one right here. So we do the move on move on cube. Move on cube needs the map, it needs the current position and direction and the translation map, the cube size and the regions. It needs all this stuff. Okay, so it takes our current position, adds direction, giving us our maybe position. Get region by coordinates takes absolute coordinates, so what we have here, and turn them into regions. So if these are 50 by 50, then this corner up here is going to be 100,0. Like the middle of it is going to be 125,25, and whatever. Like, but any coordinates in here given to get region by coordinates is going to give me 2,0. Right? So that's what it does. So it takes coordinates on the map and turn them into what region they're in, or what side of the cube they're in. But we call them regions because it makes more sense to call them sides if it's folded up, but we're not looking at it folded up here, so regions. If the maybe position, if the position we would move to, if we just added the direction, if that is part of a valid region, then we're fine, we're done. We just return the position and the direction. We don't change directions. It's just easy peasy. Cool, that was the simple case. Now, what we do instead, if it's not that easy, we get our from region by using the same function here, and then we use the translation map to translate the from region and direction to the new region and the new direction. Now, in the translation map, we have this right here going that way, mapping to this right here going that way. So if I'm moving that way, I'm going to appear here going in the opposite direction of what is recorded at in the translation map, because the translation map says it's the bottom edge of this one and the left edge of this one. But yeah, if you're coming from here, you're going to end up going that way. And that's what we have here with the new direction. Okay, so far so good. Next thing we do is we get the index of the direction that we're currently moving in and what we will be moving in. And depending on, like we saw that the list of directions has, if you turn right, then it's moving one in the. We know that the direction list is constructed so that if you move one forward in the list, that means that you've turned right, and opposite. That you get the idea. So we can use these two to determine how many times we have to rotate 90 degrees. So that's what we do here. So we start by calculating the relative coordinates of the new maybe position. Okay. Relative coordinates are, so like in this one, I said that the middle of this one is going to be 125,25. That's the middle of this right here, using the coordinates from the entire map. The relative coordinates of 125,25 is going to be 25,25, right? So if it's the coordinates within this region that we're looking at. Now, if we're at the edge of one of these, let's use this example. If we're at the edge of this one and we are moving left, the relative coordinates of the maybe position that we're going to is going to be out here, right? So it's going to be -1, whatever. So these might be, these are going to be out of bounds, basically. They're going to be either have negative coordinates or coordinates that are greater than or equal to the cube size. So we get the relative coordinates. Then we use like this little trick here, which is basically taking, saying the y coordinate is the old x coordinate, and the x coordinate is the y coordinate starting from the other side. So as an example right here, we know that this here is, this point right here at the edge is 0, let's just say 40 in relative coordinates within this region right here. If you want to change those coordinates so that you rotate them once, so that would move this one over here. That means that the x coordinate become, what the y coordinate was here, like the further down you are, the further over you're going to get, right? And then in the other direction, you start from the other side and move up or down or left, right, wherever, right? That's what we do here. So for each turn, we transform the coordinates like this. And then using those new coordinates and the new region and the cube size, we can get the absolute coordinates, and we return those with the new direction to part B, which is way up here. Okay, so that returns our new position. If that's a wall, we break, right? We don't perform the move, we just remain where we are, and that's it. And again, like a lot of assertions just to make sure that I haven't messed up somewhere, making sure that where we are going is a dot. Because otherwise something has gone terribly wrong, because we would end up in like one of these undefined parts of the map. And if all of those checks pass, then we update our current direction and our current position based on the new direction and the new position. Turning is just like before, and then finally we can get our score. But yeah, take a look at this nonsense here. Geez. Yeah. Took me a couple of days. I had some catching up to do when I got to day 24 and 25, but I got there, and I will walk you through that in the next video. But this was it for day 22. If you have any questions or comments, if you have a better way to do any of this stuff, I would love to hear it. But this is what I came up with. It's not great, it's not pretty, but it works, and it's even reasonably fast. Wow, that took a long time. Didn't used to take that long. Anyway, it's fine. It was yeah, this was interesting. There was a lot of, there was not a lot of help to get from the outside world. It's not like I don't know. I never learned algorithms dealing with cubes and how to fold them and stuff like that. So I just had to figure that out. Yeah. Anyway, yep. I hope this was helpful. Or if you have a better way to do it, I would love to hear it. Leave a comment. Otherwise, just like and subscribe, and I will see you in the next video.